Hello everyone and welcome to the third episode of the Observability Talks stream and podcast. So it's been a month since we've been around. You've missed this lovely face and voice. I'm sorry if you haven't. You're going to have to suffer with it for how long it takes to get through all of the agenda today. And as usual, we are following the usual practice of having a talk or discussion. In this case, it'll be a talk from Matt Schallert from Chronosphere, and he's going to be talking on M3DB and Prometheus. And then we're going to be covering some bits of news that have popped up in the last month. So for those of you who are tuned in, please feel free to ask questions. At the end of Matt's talk, we will be raising them. So if you haven't been around for the podcast before, this is a podcast about open observability. That means open source observability. That means we're going to be covering in later sessions everything from DevOps, observability, and the open source that glues it all together. So let's begin. I am Mike Elsmore and I am your host. And now I'm going to be dragging in Matt so that he can say hello. Hello, Matt. How are you doing?
Good. How are you, Mike?
I am buzzed off coffee, and that is a fantastic feeling. So you work at Chronosphere. Who are Chronosphere?
So Chronosphere is a hosted metrics and monitoring platform. We kind of focus on large-scale, high-throughput use cases and trying to do that all in a cost-efficient way. And we do so by building on top of M3. Which is this open source project that we're very deeply involved in and help maintain along with Uber.
Okay, now here is the important question. How in the heck did you get into the DB side of these observability world, which is full of tools? How did you end up in the data layer part?
Let's see, I guess kind of by happenstance. So before working at Chronosphere, I also worked at Uber as an SRE on their metrics platform, and kind of saw what it took to scale a metrics platform at Uber's levels of growth over many years. And a big way that we did that was by creating M3 and releasing it to the open source community. So take it as a judge of my character in one way or another. I've voluntarily chosen to work on metrics platforms for the past 5+ or possibly 5 or so years of my life. But that's how it goes.
Okay, considering you have a huge smile on your face still, it's going good for you then.
It's definitely been a lot of fun. I've seen a lot of different perspectives on how people are putting metrics to use and kind of what it takes to get the most value out of them. So it's definitely been a fun experience and some exciting learnings I'm looking forward to sharing with the stream today.
Fantastic. That's great to hear. So if you're ready, would you like to start?
Yes, let's do it.
Okay, I'm going to drag in your slides and remove myself. Have fun.
All right. Let me get this up. Thanks everyone for joining. Thank you, Mike, for having me again. As Mike kind of said, my name is Matt Schallert for all of our viewers and listeners. And I'm excited to be talking to you about Prometheus, scaling Prometheus, and how this open source project that we've mentioned, M3, fits into that picture. So we already kind of covered this, but in terms of how I ended up here, I now work on infrastructure at Chronosphere. Like I said, kind of building this large-scale metrics platform. And previously, before that, I was working on the in-house metrics platform at Uber. But I'll kind of gloss over this since we just covered it. So let's jump right into the exciting stuff. Let's talk about something we might all be familiar with, given the topic of today's stream, Prometheus. So Prometheus is what many would consider to kind of be the de facto open source metrics solution for getting your metrics stack up and running. And it's earned this title by being an all-in-one solution. So that it kind of encompasses a lot of different parts of a metrics platform. So Prometheus is both an exposition format for emitting your metrics from an application, as well as a solution for gathering those metrics, querying them, and also has an alerting component that you can kind of constantly alert on them and take action. It's really easy to get started with Prometheus, and a large part of that is because it's all encapsulated in a single instance. So that is, by default, all of your data is gathered from and stored on a single instance. And a lot of you who maybe haven't operated or worked with Prometheus directly might kind of still have seen its reach in the ecosystem when a lot of open source projects that you might run, if you hit their /metrics page and you kind of see a bunch of stats coming out, a lot of times that is in the Prometheus format. So in one way or another, you may have come across it before. But this fact that Prometheus is a single instance is kind of its strong point, because it makes it really easy to get started. And it's really helpful from an operational perspective. But like everything, it does come with some trade-offs. So to give you an idea of some of the challenges associated with having a single instance running, imagine you're running your infrastructure and you have a few services, and you decide that you want to use a single Prometheus instance to store metrics for all of them. This is totally reasonable. This is pretty much how everyone gets started. And if you can run this way forever, then that's more convenient. But over time, though, maybe one of your services grows. This might be because it's getting more traffic, or maybe you're emitting more metrics, you're running more copies of it, what have you. But either way, at some point, maybe it's beginning to overwhelm what a single Prometheus instance can gather and store and query. Prometheus offers some knobs here to help you store less data. So there are two things that mainly come to mind are relabel and drop rules. So this allows you to transform certain metrics on the ingest path, or just not store certain metrics at all. And this does buy you some headroom, but you still in storage and querying, but you still have some computational overhead either way in actually scraping the data and gathering it. So you've reached this point where you're starting to overwhelm a single instance with all of your services. What do you do now? So one pretty reasonable option is just to split things up and add a second Prometheus instance and to send all the metrics from that larger service that was overwhelming it to a dedicated Prometheus instance. So now you've solved this problem, you've bought some headroom, but you've introduced an additional challenge, which is that you now have to manage which Prometheus instances contain data for which services. And there's no one way to split this up, or one right way or something. There's a lot of ways that you can kind of shard Prometheus. So maybe you'll have dedicated Prometheus instances for certain services. Maybe you'll divide them up by team or by some other dimension. But either way, in addition, in kind of introducing this scale factor, you've also added some operational overhead in terms of managing these instances and choosing which targets get scraped by which. Additionally, you now also have multiple instances to query from. So before, when we were talking about having one Prometheus instance, you could pretty much get a global view of your metrics by querying that one instance. But now if you want to, say, query metrics across different services that are stored on different Prometheus instances, you have to query multiple. And even more importantly, what happens when a single service when a service outgrows what any single Prometheus instance can handle? Do you make changes to your service to emit less data? How do you decide what you want to throw away? Again, kind of one right answer there. And then finally, there's the question of what you do if a Prometheus instance fails. So if you only had one Prometheus instance scraping your service, you're losing data while that instance is down. One pretty reasonable option is to just have more than one Prometheus instance scrape each target for high availability. This helps with data redundancy, but now you kind of have to figure out how you'll query both of those instances, like we also just talked about. But in this case, you have to figure out if one was down and missing data, how do you kind of stitch together the data? And one thing to note, though, is that it's totally possible that this isn't a problem for you. Maybe you're scraping some low priority target and you don't really care if you have gaps in your data because it's operationally not worth it to have this redundancy. But what I've personally seen is that as Prometheus usage has grown and people are using metrics for, or people are relying on metrics more in general, they're capturing data that they might really care about having available all the time. So maybe you're capturing business metrics, or you're capturing metrics that feed into auto-scaling systems. These are things that you don't really want gaps in. So again, it's important to remember that in all of this, different users have different priorities, so it really depends on your context. But there are a growing number of use cases where not having your metrics always available could be problematic. So to recap, if you're starting out with Prometheus and expect to see your usage scale over time, there are these two main questions you have to deal with of how to handle data growth and how to handle instance failures. As I mentioned earlier, though, the Prometheus developers chose as a design constraint to focus on single instance storage. And this isn't a bad thing. It's made operating Prometheus much easier, and it allows them to make the best decisions for their use case. And obviously, it's gotten the project extremely far. The project explicitly decided that they would support long-term storage by providing an API between Prometheus and remote systems. And these are known as the remote read and remote write APIs. The remote write API, which we'll talk about first, allows Prometheus to act as a bridge between targets exposing metrics and external systems. So third-party systems can implement this HTTP API, and then you just configure Prometheus to send samples to them. And in this case, Prometheus has to only store a minimal amount of data itself, mostly just enough to buffer onto the downstream. And then it will handle sending all incoming writes to whatever your long-term storage is. Sorry, I'm getting an error on my slides here. Sorry, I'm not sure why that didn't load. I'm just gonna reload this and go back to here. Okay, and we're back. So Prometheus has this remote storage API to send data to long-term storage. And there are quite a few remote storage systems. Some offer read and write storage, some offer just read, just write. You can see actually Julius Volz's talk from the OpenObservability conference for what some of these are. But obviously the one that is near and dear to my heart that we're here to talk about today is M3. So M3 is an open source metrics platform that has all of the dependencies you need to run a metric system. This includes a distributed time series database and index, a query engine, and an aggregation tier. M3 implements the Prometheus remote read and remote write interfaces, along with some other protocols you might be familiar with, such as Graphite and StatsD. The two primary goals of M3 that, or two of the primary goals of M3 that make it well suited to be a remote storage solution are that it's highly available and it's horizontally scalable. So let's take a look at that first part for a second, the high availability aspect. So high availability in the M3 ecosystem is handled by M3DB, which is the core distributed time series database and index that kind of sits at the foundation of the M3 stack. M3DB takes care of sharding and replicating your data across different failure domains. So this can be zones in a cloud region, this can be racks in a data center, or this could be cloud regions across a continent or multiple continents. In this case here, for example, we have a 9-node M3DB cluster with spread across 3 zones in the cloud region with 3 nodes in each zone. So M3's cluster membership algorithms take into account the failure domains of each node and distribute shards accordingly. In this case, with a cluster with a replication factor of 3, each zone would have a full copy of the data, and each of the nodes in that, each node in each zone would own roughly 1/3 of the data set. Within M3, there's also a component called the coordinator. This is kind of what we refer to as a fat client that handles reads and writes. So what this means is that as the coordinator, as incoming writes come to the coordinator, it will take care of sending those writes to all 3 replicas. And the coordinator itself will decide which ones succeeded, which ones didn't, what counts and doesn't count about as quorum, handle retries, etc. This is as opposed to having like the database, for example, handle replicating each write to its peers. So if you're familiar with a system such as Cassandra, there's this concept of hinted handoff where a database will get a write, and if it has to forward it along to a peer, it will, if it has to forward it along to a peer, it will. In M3DB or in the M3 ecosystem, it's all that logic is just encapsulated in the coordinator. This puts less load on the database nodes, and it also means that we can scale the coordinators statelessly. So, depending on what sort of data you're sending, you can actually have cases where like ingest might become more computationally expensive, and you don't have to worry about scaling your database just because you need more capacity in your ingestion path. And then from let's say you have a failure in a zone. So for example, in this example we were looking at where you have 3 zones, let's say you actually lost an entire zone. M3DB has quorum, reads, and writes. So in a cluster with a replication factor of 3, you would only need 2 replicas available to serve reads and writes without any errors. In this case, we see that we've lost an entire zone, and it doesn't matter whether we lost the entire zone or just some nodes in it. Clients writing to the system won't see any read or write errors, and their data will remain fully consistent. If you lose nodes across more than one failure domain, admittedly, then it's harder to uphold these guarantees depending on the shard or depending on the ownership of the shards of the nodes that failed. But actually, as long as you still have one replica available, you can serve potentially inconsistent reads. But again, in this kind of like more common failure scenario of losing nodes across one failure domain, there's no interruption to the end user. I see a question here actually on Twitch. How does communication between the nodes work when they have a failure in a multi-DC setup? And how much does the latency affect the repair? We'll get actually in a bit to the concept of peer streaming, and I'll kind of revisit this, and we'll talk about how some of the repair and redistribution of data works, but this is a good question. So let's think back, let's talk about horizontal scale now. We've kind of covered how M3 achieves high availability, and as I said, this other goal is to be horizontally scalable. So thinking back to that situation we mentioned earlier where you're emitting metrics from many services, and let's say you have a 3-node M3DB cluster or like 1 node in each zone. One of your services gets too large, begins overwhelming your cluster, and you pretty much just have to add more M3DB instances to kind of like handle that scale out and distribute your data evenly. That's kind of a high level overview. And if we look at how that works on a per node basis, it's all achieved by this notion of, or by what we call peer streaming. So let's say you started with a 3-node M3DB cluster, and each node owned 30 shards. You begin to you started to reach capacity on that, whether depending on your ingest patterns, maybe you wanted more disk capacity and you had fixed disk sizes, or you needed more memory. But either way, you need to distribute the load across these nodes. So in this case, the cluster membership algorithms, when you add these new nodes, would decide what the new optimal shard distribution would be, and publish that kind of desired state into the cluster. And then the nodes themselves will work to converge on that desired state. So in this case, we want each, if we're adding 6 nodes total to what was previously a 3-node cluster, then we want each of the new nodes to have 1/3 of their replicas data, and they will begin gathering begin streaming that data from the nodes that owned it over an RPC mechanism. Once those new nodes have determined that they have streamed all the data and they have a fully up-to-date copy of what the previous nodes had, they'll mark themselves as successfully having received copies of those shards, and the new nodes will stay available for that shard. And then once all the shards are available, the old nodes will drop the data, and you'll have an evenly distributed set of an evenly distributed set of the shards across all these 9 nodes, and have more capacity. And so this is where, when we kind of think back to that, how does communication work between nodes when they have a failure in a multi-DC setup, and how much does latency affect the repair? So in the base case, when an M3DB node fails, you actually don't need to receive or to get copies of the writes that it had while it was down. This is where we kind of rely on those quorum semantics, and we typically run with odd replication factors at least 3. So as compared to a setup where we have, say, 2 replicas, and it might be more important, or we only have 2 copies of data, and it might be more important to catch up on what you missed. In this case, we actually just assume that 2 copies were up at or at least receiving writes at any given time, whether or not they were fully quorum. And you don't need all nodes to, say, own a complete copy of the data set and do any sort of ongoing repair operations. But in terms of, say, you were just running these across multiple DCs, if you really wanted to distribute the data across DCs, then when you add these new nodes here, for example, and they begin peer streaming, you could just put these new nodes you're adding in different data centers and mark them as being in that data center, and they'll get the shards distributed according to those failure domains. So we talked a lot about the kind of write path and getting data into your system, but obviously getting data into your remote storage is pretty useless if you can't also get data out. So the other side of this Prometheus remote storage ecosystem is the remote read API. And this is actually a bit trickier than remote write. Remote write, you're pretty much getting some samples, storing them on disk somehow. Remote read, you actually have to be able to answer more complex queries. So in the remote read path, you'll first send a query to Prometheus in PromQL, which is its native language. And Prometheus will take care of parsing this query, and rather than executing it locally, will instead send some metadata to your remote storage API. Among this, there are a few fields in this metadata request, but the most important part is the set of label matchers. So Prometheus might send you something like, get me all time series where tag A equals value A and tag B matches some regex. And then your storage system will return all the time series that match, and Prometheus's query engine will compile that response and send it back, and send back the response to that PromQL query to something like Grafana for visualization, or maybe your alerting engine. So M3 also implements this remote read API. So we have this other component called M3 query, which you can actually just run in the same binary as the coordinator process that we mentioned earlier. And we actually have 2 different approaches to how you can get, or a few different approaches to how you can get queries through mQuery and into the M3 ecosystem. So you can either into the M3 system. So you can either use the remote read API, in which case we will, match those, return the time series that match those label matchers that we see here, send them back to Prometheus instance to compile the response. What we've also done is you can also we have imported the same PromQL implementation as upstream Prometheus. So you can also just send a PromQL query directly to M3 query, and we'll run it through the Prometheus query engine, just to kind of like save a hop there and have a bit tighter integration with our storage. And then finally, we also have our own implementation of PromQL. However, it optimizes for performance and not as broad set of use cases, so it's not guaranteed to be up to spec, since we've kind of had to make our own trade-offs there. But one thing that we've heard from users that they enjoy is kind of this ability to make their own compatibility trade-offs. So depending on their query cases, maybe they don't need like 100% PromQL compliance and can kind of get like a little bit more performance out of it for better integration with M3, or maybe they do want that full PromQL experience and ensure that they have full compatibility. This is actually something that the Prometheus community has been looking at a lot recently. So there was a report, I believe, from PromLabs on PromQL compatibility across different projects that we're going to attempt to submit our results for. But again, since we understand that both the Prometheus community and a lot of end users do want that ability to have that full native implementation, so we offer that as well. So in terms, we've talked a lot about M3 and its role as a remote read and remote write API, but obviously there are a lot of other options in the ecosystem. So just to briefly talk about how M3 kind of compares to those, and we can dive more into this in the discussion a bit if we want. So the main difference is that from what I've seen versus a lot of other projects is that M3 really is like the full stack solution to, or full stack storage and query layer for storing and retrieving your metrics and for interacting with Prom. What I mean by that is that when we talked earlier about M3, redistributing shards and kind of like doing all this cluster membership, is that each M3DB instance has the copy of the data on its disk and handles the quorum semantics kind of transparently from the users, or kind of transparently to users. So compared to something where you're using like external storage, whether it be maybe like a more generic database that's not necessarily built for time series storage, or something like a hosted database service from your cloud provider, compared to these where you're kind of offloading some of those storage needs to an external system, M3 really has, really owns the data. Pretty much all you need is like some disk, CPU, memory, and a network, and you can have an M3 stack. Similarly, because we have all this have all the data on our own disk and have been able to kind of like optimize for that case, the fact that we also have this embedded index, it allows for very fast queries, or allows for very fast index queries, especially since it's built on top of a technology called like FSTs that allow for really fast regex lookups. So if you're doing large regexes over a large data set, each node can kind of like map, almost in MapReduce style, gather the data on disk that it owns and return those results much more quickly than, say, like iterating over all the series that match some tag and figuring out which match your actual query. So these are some of the benefits. Admittedly, there are operational trade-offs as well, and I hope that as you kind of gather from a lot of things we've talked about today, there is no one right answer for everyone for any of these problems. There are some operational trade-offs you have to make if you want to kind of own all this data yourself. Compared to, and just looking at like one other example, say compared to a solution where you're using like cloud storage, like an object storage, for example, to store whether like just the actual data blocks or metadata, comparing a system like that with M3. So, with M3DB, again, you kind of like fan out these queries to each of the nodes. They run the data, or they run those queries through data that they already own on disk and can kind of like quickly return a response. Whereas with something, if you are, say, offloading that storage to like a remote object store, you have to fetch those blocks on demand. You kind of have to like iterate over the metadata that matches your query, and there's just a little bit more back and forth. And there are non-trivial storage costs for like storing data in an object store, but also for retrieving the data and kind of like all the network costs that come along with that. We've talked a lot about, once you have M3 up and running, and I'll kind of just briefly talk about how you can deploy it specifically. Like, we've seen a lot of folks in the community have interest in and success with running M3 on top of Kubernetes. So what we did was create like an operator, an open source operator for Kubernetes that allows you to kind of define these higher level cluster attributes that you want, such as you want a 9-node cluster across zones A, B, and C with 1,024 shards and a terabyte of disk each. And one thing that's really nice is that since Kubernetes also has the concept of like failure domains and expressing these requirements and letting you know kind of like where pods are placed, and also you telling it where pods are placed, then you can, with the operator, you can pretty much like say that you want this higher level cluster state. It'll ask Kubernetes to schedule these instances according to these specific requirements, and then you can do things like maybe you want to weight your shards based on memory, or you want to ensure that you have certain disk types attached. Obviously, Kubernetes introduces another layer of complexity that you kind of have to, or that you're probably not going to get as much success with this setup if you don't kind of know some of the pitfalls there. But if you are more familiar, or if you are familiar with that, you can kind of like merge these two ideas that M3 has of like shard distribution, failure domains, with the similar controls that Kubernetes gives you for that. So that's about all I have. I hope that this has been a helpful overview for you all, and excited to have a little bit of discussion about some of the topics we talked about. If you're interested in learning more, check out some of the M3DB open source resources we have. So M3DB.io is our project homepage. We have a community Slack linked to from there where we're pretty active. Our GitHub organization is just M3DB, and our mono repo is at M3. And as I mentioned earlier, I work at this company Chronosphere that's built on top of M3. And if you have any questions about Chronosphere or interested in learning more, our website is simply chronosphere.io. So now we will kick it over to Q&A. Let's see.
There we go. So I'll drag myself back in to help with these Q&As.
Hey,
right,
Mike.
We have some from the crowd. So yay, crowds.
Great. So I will talk about, let me take these in order from those we haven't covered. So how do you balance cap when recovering from node failure? So this is kind of what I was talking about, or I somewhat touched on this earlier when I said that, we don't necessarily we don't expect each node at any given time to always have a full copy of the data set. So if there was a node failure, rather than trying to make sure that like each node has as best view of the data set as it can, our assumption is that at any given time, there were 2 up for any given, or for any shard. And we kind of just rely on that for quorum semantics. M3 actually has tunable consistency guarantees. So if you want, you could even say like all 3 nodes must, or all replicas must require or must acknowledge all shards if you are running. And then when nodes bootstrap, which is kind of when they come back from a restart, you can also add some more consistency guarantees from there in terms of like which parts of the data they own. We actually have a doc on our website, or sorry, a section on our docs, which is docs.m3db.io, called Tuning Consistency and Availability Guarantees, I believe. So if you're interested in more of those, or if you're interested in more of the details there, I'd encourage you to check out that section. This next question is, are you running the newly released PromQL correctness tests on M3DB? Any data you can share? We plan to. I believe we've actually talked with some members of the Prometheus community about getting that up and running, but we plan to run that ourselves. We just haven't done so yet. So I think those came out like a few weeks ago. As I said, we built this, our implementation with these trade-offs in mind. So I don't necessarily think it's, at least right now, one of our goals to have 100% compatibility, because in some cases we do make performance trade-offs. But we're excited to see this effort in the community around kind of like getting better visibility into these different implementations. And so we're going to work on getting our results up for that as well. This next question is, which parts of Cassandra inspired the design of M3? So yeah, I'm not sure if this is kind of with the specific context in mind that as Uber has talked about in a bunch of their talks. So M3DB was actually built to replace Cassandra. There are actually some operational perspectives of Cassandra that the kind of opposite of them influenced M3. So for example, our cluster membership is all stored in etcd, and it's kind of like this external cluster membership. We have had some pains before with running large scale gossip systems, especially across multiple data centers, or even if you have like zones with unreliable links within single regions and such. Yeah, also just the fact that, Cassandra is more of a general purpose key value store. So if you're storing like timestamp value pairs as you are with time series, then you are like pretty much storing whatever, like, 64 bits for like the timestamp, 64 bits for the value or something. With M3DB, it uses a compression algorithm called M3TSZ, which is based off of Facebook's Gorilla compression. And so you get like 11x compression or better, depending on your kind of data patterns, compared to just storing like raw key value or timestamp value pairs. I've seen a lot of discussion on the aggregator. Can you explain the current and plans for aggregation? So right now, the aggregator is arguably one of the more operationally complex parts of the M3 stack. So I didn't go into this too much, but our aggregator is this open source aggregation tier that's fault tolerant and allows you to do kind of like complex aggregations on incoming writes to save on data costs. So if you're familiar with Prometheus recording rules, you can pretty much think of the aggregator as like a massively scalable, fault-tolerant recording rule tier. And this fault tolerance is achieved by having like 2 copies. So there's 2 replicas running at any given time. They use leader election, and only one of them is like actually writing out data at any given time. But anyway, because of some of these design constraints and just some of the complexity around aggregation in general, like I said, it is pretty complex to operate. There's a lot of, you have to kind of keep in account or take into account like timing of things like restarting instances based on your aggregation intervals. So we are exploring things such as maybe having aggregators like stream data to each other in the event of failures, rather than expecting each one to always have a copy of the data. Right now, though, for our users that are running the aggregator in production, it is working well for them and their use cases. Since it's not as commonly used as some of our other components in M3, at least right now, we're working on like simplifying M3DB operations and kind of some improvements there. And we're going to, we're kind of going to revisit the plan, or take another look at the plans for the aggregator based on kind of like community feedback and usage of it. Where is the open source M3 project going in terms of software foundations and governance? So right now, the governance committee is partly made up of Uber employees and partly made up of Chronosphere employees. And then other contributions come from the community and go through Uber's CLA process. Right now, there are no plans to contribute M3 to any software foundation, and kind of just going to see what the community wants and where interest lies there. But there hasn't been, any, that hasn't come up too much yet. And yeah, so at least right now, no plans. How does M3 handle backfilling? So this is actually something that this is another area where we kind of worked on this later on in the project's life based on community feedback. So M3's original use case was designed for just incoming time series writes where you're pretty much always collecting like current telemetry, and there hadn't been as many requests for backfilling data, or it really just wasn't the primary use case. Over time, as M3's adoption has grown, more folks are coming with these use cases where they want to be able to write time series data into the past. This is initially something that wasn't part of our was difficult to do with our design because in M3DB, all blocks other than the current block are typically immutable. So we actually in the past year introduced cold writes, which we kind of revisited some parts of the storage engine and made it actually possible to write data into previously closed blocks. So right now, to backfill data, you just pretty much write it back into the past. And if you have cold writes enabled in the namespace that you're writing to, then you can actually backfill some of that data. So this is kind of another example where we initially built M3 with certain design constraints, got some community feedback on features that folks wanted, and we're able to incorporate that into the process and build that out for folks, which is really exciting.
Wow, we went through those.
Cool. Yeah. Wow.
It's fine. I have another one that I was just thinking about. So M3 has been designed as the long-term storage option for Prometheus-based metric data. Now, my brain was just wrapping around the whole rebalancing process of the nodes, which I love the fact that it's the sharding methodology means that it's not trying to run active communication on nodes that haven't rebalanced. It's great. But that means the more nodes you add, you're going to end up with larger distributed shards across all of them, just because the very nature of adding more nodes to a cluster. What happens when we enter the realms of thousands and thousands of data points and we need to do sampling? Is this going to be a point where we're going to require the individual node to do a subsample before having the coordinator do a superset sample of it? Or are we going to be requesting the entire data set period and then have the coordinator just essentially destroy through memory requirements to actually create samples from there? I know we're not quite there yet because we're not producing enough data, but
yeah, you would think that there are actually active use cases in production where where this has come up. So the way that we handle this is kind of through aggregation and pretty much handling sampling on the write path. This is something we've started to look at and is potentially on our roadmap for handling wider read side aggregations kind of on demand, and we've started to do some work there. But at least so far, the way we handle this is you have namespaces with different retention and resolution configurations. So for example, in a single M3DB cluster, maybe you're storing 30 days worth of data at 10 seconds, and then you're storing 5 years worth of data at 5, 10, 30-minute resolution. This is achieved the most reliable way to achieve this with full data fidelity is through the aggregation tier. So you pretty much just write certain data or certain samples. Sorry, incoming writes come in, you aggregate them, and you send them to different namespaces depending on the retention and resolution configuration. And one thing that's kind of nice about this model is whether you have multiple namespaces in a cluster or multiple namespaces across different clusters, one thing you can do is say in your long-term cluster, there's less data you're storing, it's less kind of demanding on the write path. So maybe you actually run that cluster on, say, spinning disks and kind of like save some disk costs there. And you kind of keep your like active or hot data on more expensive disks. And so it's kind of nice to be able to make that trade-off of disk requirements and memory requirements and such based on the pattern of the data that you're storing. But to answer your question, we typically handle these sampling on the right path at aggregation time.
I am going to be very, very curious when people start building long-term predictive models on this data. It's going to be very interesting how people start actually building those data sets.
They are out there.
Pardon me?
Yeah, there are use cases that are using M3 for pretty, historical like data analytics use cases like this already. One thing that we're excited about is we've started to kind of get more folks in the community talking about their experience running M3 outside of some of the common use cases that you've seen. So hopefully over time you'll be able to hear more of those stories as well. And actually, we have a open source M3 meetup that you can find on our website as well, where we are running similar to what we're doing here every so often, and having more folks from the community talk about their experiences.
Okay, that is amazing. I'm just going to quickly, this is going to be from the M3DB website, correct?
Yeah, let me see if I can find it.
I am
M3.
just grabbing it now so I can share screen and
here, I'll tell you what, I will send you.
That sounds fascinating and something that we should definitely share for people to get involved with.
I just sent you over private chat, our virtual meetup group.
Okay, here we go. Let's open that and share screen. So here we go for those people who have just, oh wow, it's an actual, geez. Okay, so a proper community-orientated meetup for discussion on these edge and long-term use cases for M3.
Yeah, so this was one specific instance of it recently, but that group is where we'll be posting, our future meetups as well. So hopefully you can hear about some of those other use cases we've discussed.
So everybody who's tuning in now or listening to this much later in the future, Google Meetup M3 Community, and it will hopefully bring this up so you can find it yourselves. I will remember to add this to the description of the YouTube video afterwards so somebody can find it as well. But that is absolutely bloody brilliant. We do actually have another comment. Here we go. So that's that. Do you want to take this one? Or is
Yes. Yeah. So pretty much the aggregator. Well, it is dependent on how you configure this. So if you want to just do kind of like basic sampling and rollups on the right path with the coordinator, you can. But for those kind of larger scale fault tolerant use cases, that's where the aggregator comes in.
Okay. And for those of you who can't see this, the question read, is M3 taking care of downsampling and rollups? As a follow-up question to my awkward question for Matt earlier. Okay. Is there anything else you would like to share, sir?
No, I think I covered some of those links previously. Would encourage folks to check them out. If anyone has any questions, would love to chat further in our community Slack as well.
Feel free to send over the link to that, and I will drop that in the video description as well.
Definitely.
Fantastic. Right. Thank you very much, Matt. It has been an absolute pleasure. And I'm going to drop you out of this so that I can start with the breaking news.
Great. Thanks so much for having me, Mike. This has been a blast.
Absolutely. Fantastic, Matt. Right. So, as always, the breaking news. I discovered how to use a mic properly for these effects. It's fascinating. Right. So, there has been some stuff this week, and share my screen. There we go. But there has only been two big pieces of information that I have come across. If anybody in the chat has any other big news in the open source observability and DevOps space, please feel free to share. But the biggest ones that I have seen is the release of the 7.9 set of the ELK Elastic Stack setup. And this is increasing a lot of the capabilities in Elastic Cloud, but it's also putting a lot more work into Elastic as a whole. And I'm very curious about how the upgrade path is going to be with everything, just due to the amount of components that have been upgraded at once in this release. I'm curious about the upgrade path for it. I personally haven't tried yet, and I'm not going to lie, I'm a little bit scared of doing it. So there we go, big release, and that was last week on the 19th. And there is also some big pieces of news from the vendor space as well. So Sumo Logic is expanding their observability platform. As one of the bigger people inside of the observability space, this is quite big news, because they've focused primarily on the enterprise side of things. With an increase in their SaaS offering, that means hopefully a little bit more of a push for the smaller people. And in my eyes, they've already put it here, more work within the open telemetry. That's fantastic, because the more organizations that get involved with the open telemetry space, the more feasible and easy it will be for end users to implement, and people to just pick the right piece of software to do their work as an operator. So I think that is fantastic. And on top of that, which in my mind, if open source projects always need a little bit more help, they're also looking to go and get their IPO, $100 million. You know what? I think the scene in The Dark Knight, where he slides down a pile of cash, is exactly how I imagine that to be, just that large sum of money. But this means they're going to have a lot of money, which means, in my opinion, and my hope, a little bit of that means they're going to be able to put full engineering cycles into the open source side of life, which I think is brilliant, because as Sumo Logic and companies like Splunk, who are these big incumbents who've been working in the enterprise and the large factor space, get involved in it, the more level the playing field is going to be with processes and plans like OpenTelemetry to build better software. So that is all the breaking news we have, because surprisingly, I'm really bad at finding news. I could do some help. If anybody on the internet sees interesting things over the course of the month, feel free to tweet it at me, which is at UKMadEls, or send it through to any of the details on the Open Observability website, where you can post when it happens and how it happens. So that is today's Open Observability Talks episode. Thank you very much for joining us. Thank you very much to Matt for sharing, well, a long talk with a lot of information and an even longer amount of questions. I'm sorry that we got him with so many, but I'm really glad he answered all of them like an absolute pro. So thank you very much, Matt. So that's us. This is the OpenObservability.io website will contain all the future and previous episodes and any upcoming stuff we do. If you've missed out and you want to be able to get involved in later episodes, we will be on every Thursday. The time will depend on who we are having speak, obviously. And it's at twitch.tv/openobservability. If you want to follow us along in general on Twitter, we are twitter.com/openobserve. And you can just get all the other details on the website. And if you have an interesting topic you would like to share with us, on screen is the Google form to drop a CFP so that we can host you and show off your knowledge and information to the world. It will also be in the description below, so please feel free to click that and share your knowledge. So I've been Mike Elsmore. Thank you very much for coming along for this little ride, and I will see you next month. Goodbye.